All right, just a overview of the assignment or the activity correlation and regression wisdom. The whole point behind this one is to get an idea of when you have a regression equation or a correlation coefficient, get an idea of what that's telling you about the relationship between the two variables. All right, so between correlation coefficient, slope, y-intercept, basically all the stuff that we've done, plus what we're going to learn about today, which is residual plots, you should be able to make a determination of first whether a line is the most appropriate fit for a data set, and then after that, what that tells you about the relationship between the two variables. And so the first thing that we need to do is come up with these three values. I'll highlight that in yellow. And that's automatically, if you copy paste this concatenate line command, that'll automatically give you the equation in the appropriate form. So I won't highlight that because that's automatically going to be populated for you, right? So correlation coefficient equals, start typing. Odds are you're going to land on the thing that you're looking for. All right. So correlation between the y variable followed by the x variable. All right. So that gives me the correlation coefficient. Now that's a value that's very, very close to -1, which means that there's a strong linear correlation between these two variables. And now it's specifically a strong negative linear correlation, right? So in my conclusion area, well, I'm going to move this down a little bit, clean this up. This will all be set correctly for you when you get it. But in my conclusion, I'll say that there is a strong negative linear correlation between population and year. All right, we'll add on to that in a minute, but for now, that's a good conclusion to draw. And try to keep it on the screen a little bit. The slope, so equals slope. And again, you start typing it, it gives you a suggestion. Most likely that's going to be the one. The y column first, comma, the x column. All right. Now, this population is given in thousands. So this slope is giving us the change in population in thousands per year of change. Right? So every year that increases, so starting with 1945, it's saying that the population will decrease by 0.587 roughly thousand each year. All right, so I'm going to throw that in my conclusion. So the population decreases, that accounts for the negative, at a rate of 0.587 thousand per year. Okay. Now, if you want, you can make that 0.587 thousand into 587 people, but that's giving us not only the fact that there's a relationship between time and population, but it's telling us specifically what that relationship is. And you notice, so I'm going to hit enter there. I'll increase the highlighting. That's a personal preference. Right? You could use more than one line if you want. I'll throw some highlight here too, because we got to account for a few different things. But yeah, if you wanted to overflow, you could. So this is all in one cell. If I select format wrapping, I can have it wrap into the next line, but then you can kind of see how that gets a little out of whack. So maybe you don't do that, but you could also clip it so that only the first couple of letters or whatever fits in the cell would show up. I personally like to let it overflow, but that's what clipping it would look like. See, the words are still there, but you have to go up here to get it, right? So it's a style choice. So whatever, as long as it looks reasonable, it's going to be fine, right? And you see how now that I computed a slope, it popped it into my linear regression equation, right? You see references to LSRL in the directions. It stands for least squares regression line, but it's synonymous, at least for our purposes, with the regression equation, right? So So we're covering this part of the assignment by doing what we're doing here. All right, the intercept equals intercept y-intercept of the line from a linear regression equation. Beautiful. So drag, highlight, however you want to say it, the y first, then the x. Close it up, enter, and now I have the y-intercept. All right, so what that's telling me, and conceptually it's kind of weird, but if you have years, so here 1945, and a corresponding y-intercept, that's telling us what the population would have been in year 0. All right, so that's 1,945 years prior to the first value on this table. So not necessarily relevant, right? Living on American farms, where there are American farms in the year 0, who knows, So you kind of take that with a grain of salt, but you can also shift the data points if you want. Instead of saying 1945, I could define year as years since 1945 and then go 0, 5, 10, 15, and so on. That's another way of handling it. We could also truncate these because we don't need so many decimal places. If we select this one, decrease decimal places, it'll get us down. 3 decimal places is usually good enough, all right? So you could do that so they have cleaner numbers to work with here. It still keeps the actual real numbers, it's just showing you less. If you want to do this, to do it to these points, you'd have to throw a round function on each of your values. So if I wanted to throw a round in there, I could. I'm not going to, I'll just show you real quick. All right, so it would round that value. All right, it's not a problem if we work with the exact decimal form. So, truncating the decimals or rounding is not a requirement, but it's something you might choose to do. Now, for the predicted population, that's what the population would be based off of this linear model. So here's what actually happened. This column is the recorded data, and this column is what it would be if it followed this linear equation. So what I'm going to do is type in equals. I'm going to select my y-intercept. I'm going to add to that my x value. I could do it in either order. So x value times slope, or slope times x value. So either way, I'll do the slope first. Slope times whatever the year is, the x value. So that tells me that the population was 32.1 thousand, right? So 32,100 by my estimation model, my regression equation, my predictor model. They all really mean the same thing. It's telling us that it should have been 31.498. But we also got to be careful because it's not a perfect correlation. If this were a -1, it would be perfect. It's not, so there's room for variation. In this case, my references are good for the x value, but I want to lock in my references for the slope and the y-intercept, so that's my G stuff. So $signs, should be getting better and better at that as we go. The only thing I want to vary down the line is the A value, so the value in column A. All right, my suggested autofill, if I did that right, should be good, and it is. All right, so it's telling us back in 1945, there was about 32,100 people. Now in this town, there's only 7,200 people, right? So from that, we can do a prediction of a future event, right? So we're actually going to do the same thing. So for the Y value in 2025, right? So I want to be able to predict how many people will be living in this town in the year 2025. So I'll use my function model again. So this same thing here, I'm going to just grab that. I'm going to put it in and just change my reference. Instead of referencing 1945, I'm going to have it reference 2025, which I have stored in A19. So that's telling me that I'm going to have a negative amount of people. All right. So in my conclusion, I would want to make a statement that this linear function isn't always going to work. Right? So for large values of x, we're going to get y values that are not necessarily reasonable. So the prediction model fails. And we'll keep it general, so after a while. Because it will eventually start returning negative numbers. And that doesn't make sense for population. Populations? No, populations. All right. And if you want to extend, just for style, if you want to extend that a little bit, you can. All right. It's also asking us to create a graph, make a scatter plot of the data. So that should be easy enough because we learned techniques for that. It's highlight the data, insert chart. All right, make sure the labels are right. If you also highlight the column headings, it should automatically populate that into the graph as labels, and then it should give you a nice title. All right. We already found the linear regression equation and the correlation coefficient, so I would make it at this point optional for you to. You might remember from a previous assignment, we would edit the chart. You go to customize under series. You can turn on the trend line. You can label it with the equation and show the R squared. That's optional. You might find value in that just to make sure that what we did up here is correct. It gives you an R squared value. Correlation coefficient is actually R. Make a little note of that. So if you take this number and raise it to the second power, you'll get that as a result, right? But this is a pretty comprehensive regression analysis, right? So we have a relationship between the two variables that we thought was linear based off of the R value. It looks pretty linear based off the graph. We have an equation that we could use to make predictions, all right? Then what we're gonna do is create a residual plot, which I don't know where these values came from. So let me clear that out. All right, the residual plot is a plot of the difference between the actual Y values, what really happened, and what we predict would happen. All right, so all you have to do to come up with the residual is take the actual value and subtract from it the predicted value. And we can lock that in, right? So this residual is telling me that my population is approximately 607 people more than it should have been, right? So what happened is, 0.607 is in thousands, so 0.607 thousand or 607 people, or in terms of the population. So this was an underestimate, right? Our population prediction was under what it should have been, or what it was actually. This is what it should have been, this is what it was. All right, so we're predicting a lower value than what it was for each of these positive numbers. If it's negative, it means that our predicted value is higher than what it actually was. All right, what we want to do here is draw or plot a residual graph. So I'm going to grab that first entry. I'm going to just copy D3 right down here. Hit OK. It'll populate it in. We're good there. And now I'm going to make a plot containing just these values. Insert, chart. All right, it labeled it up nicely. So if it does that, there's no need to do anything else there. We have the plot. In terms of a conclusion that we can draw, if you see a pattern, a noticeable pattern in a residual plot, it means the linear model is not the best option, right? It means that some other model might make more sense. In this case, and I'll qualify that by saying, if you have to imagine that there's a pattern there, then there's no pattern there, all right? If your first impression you see no pattern, then a linear model is appropriate. If there was a pattern, like a noticeable, distinct pattern, then you would say a linear model is not appropriate, all right? So in this case, the linear model doesn't seem, I see a pattern here. Maybe you draw another conclusion, but it looks like it's got kind of a U shape to it. It doesn't have to be a perfect pattern. Like in this case, I'm looking at something that looks almost like a parabola, right? But it might be something else. This point over here kind of throws things off. Pretend it's not there. I see a pretty uh, oscillating pattern, kind of like a sine wave. If that point wasn't there, it'd be a little bit more pronounced, but it is. So it might cast a little bit of doubt. But I would look at this and say linear model is not necessarily appropriate because, and you can refer to yourself here, and I'm going to do that. I see a pattern in the residual plot. So what that tells me is that I might have to try a different regression technique. So we're doing linear regression. There's also quadratic regression. There's also logarithmic regression, other types of curves, not necessarily just lines. So this is an avenue or a reason or a justification for us to explore those other types of regressions.